Okay, we're going to get into some different techniques for solving equations. One of the techniques we can use when we have an equation of this format here that involves sine and cosine is we can square both sides of the equation. Now, one thing that we have to caution whenever we square both sides, we have to look for extraneous solutions. Okay? When we start squaring things, sometimes we put solutions into the equation or find solutions that don't work. So that's going to be something we need to make sure that we watch. But anyway, one of the things we can do to start solving this, since we have a sine and a cosine here, we really can't combine these in any way, but as you'll see, if we square both sides, alright, and I square this properly, squaring a binomial, I get sine squared x plus 2 sine x cosine x plus cosine squared x equals square root of, well, not square root of 2 over 2. That's going to be 2 over 4, or 1/2. Okay. Once we get that, we should notice a couple things from our identities in the past. Sine squared and cosine squared, those will add up, okay, to be 1. So I end up with 1 plus 2 sine x cosine x equals 1/2, and I should recognize 2 sine x cosine x as the double angle formula for sine. Now, how is that helpful? Well, it's helpful because now I have just a single trig function in my equation that I can deal with. If I subtract 1 from both sides, I end up with sine 2x equals negative 1/2. And then, similar to our review in the beginning, I have to solve, I can do my u substitution here, and I'd end up with 2x equals 7 pi over 6 plus 2 pi n, and 2x, I keep using n's, I'm sorry, this book uses k's, and 11 pi over 6 plus 2 pi k. Then, similar to what we did in the review there, the warm-up, I'd multiply by 1/2, end up with x equals 7 pi over 12 plus pi over 2 pi over 2, which will just be pi k, and the other solution here would be 11 pi over 12 plus pi k. That would be my general solution. Okay, now, before I circle that as my general solution, I need to think about this a little bit though. Let's go ahead and write out our solutions from 0 to 2 pi. If I start writing them out based on my solution sets here, I'll get x equals 7 pi over 12, 19 pi over 12, and we'll stop there with that solution set, 11 pi over 12, and 23 pi over 12. Now, what we have to be careful of here is because we squared, we're going to have some extraneous solutions. So let's just take a look at this. If we plug a couple of these back in, or we plug all of them in to our equation here, we're going to find out that we actually don't, these solutions don't work out in the equation. Mainly this has to do with the fact that you squared, and when you go backwards and you took the square root, you would get a plus or minus. Okay? If you were to check these two middle answers here, what you would find out is these two answers would not work. Okay? So from that, we're going to get x equals 7 pi over 12 and 23 pi over 12. And those would be the only two solutions that work from 0 to 2 pi. Now that's going to modify our general solutions, and so we need to come back up here and modify those there. And what we could do is just rewrite our solution as 7 pi over 12 plus pi k. I know that would be a solution because the 7 pi over 12 is, and the period of sine 2x would be pi, and 23 pi over 12 plus pi k. And those would be my only two general solution sets. Now, another technique involved here with squaring is a little different with secant and tangent. In this situation, we'll want to manipulate the equation a little bit before we square it. But again, we're going to square it, so we're going to have some extraneous solutions. We need to check those out. In this case, whenever you have secant, tangent, cosecant, or cotangent, you want to take one of the terms to the other side. Okay? Then I'm going to square both sides, which is the part that we're doing here. Okay? And secant squared is, by the Pythagorean identity, 1 plus tangent squared. If I square this binomial properly, that's what I get. Now, I change the secant squared to tangent, 1 plus tangent squared, because I'm trying to just get all my trig functions the same. What's nice here is if I start subtracting, if I subtract the tangent squared from both sides, they cancel out. Subtract the 1 from both sides, they cancel out. It's going to leave me with 0 equals negative 2 tangent x. Or, if I divide by negative 2, tangent x equals 0. Well, tangent x equals 0 when x equals any multiple of pi. So we can just say it as pi k. That includes 0. So we need to check that out. And before we circle this and make it our final answer, we need to check out our extraneous solutions. So I'm also going to list quickly here my solutions from 0 to 2 pi, which in this case would just be 0 and pi, and then I need to check those out. Now if I plug those back in here, what you would find is x could not equal pi. What you would get is negative 1 equals 1. So that doesn't make sense. So my only solution here is going to be x equals 0. Alright, from 0 to 2 pi, and that would modify my answer up here. The next time tangent would have a solution in the general case, or I'm sorry, this equation would have a solution in the general case is when we have 2 pi k. Alright? It's every time the angle hits the 0 position. And that's it.